For a recent year, the following are the numbers of homicides that occurred each month in a particular city. We're to use a 0.05 significance level to test the claim that homicides in a city are equally likely for each of the 12 months. Okay, so equal likelihood, that's our null hypothesis, is that homicides occur with equal frequency in different months. We want to test the police commissioner's claim that homicides occur more often in the summer when the weather is better. Okay, so there's at least some month where the frequency of homicides is different than the rest of the months. So our alternative hypothesis, will be at least one month has a different frequency of homicides than the others. Now we're not going to assume this one because that's a particular number that we don't necessarily want to mess with trying to test. We're just going to test for now that at least 1 month differs. I've used the table to open the data in Excel, and I have now a table giving me the frequency of murders in each month in that particular city. Now, if they were occurring with equal frequency, I would expect the observed value in each month to be approximately equal to that of the average. So I'm going to go ahead and calculate the arithmetic mean using the average function. And this is approximately the number of murders I would expect to see in each month. So what I'm going to do is I'm going to copy that and paste that value into this box and bring it down this column so that I can use it to calculate for each of my observed versus expected values. So in order to execute the test, we need to calculate our chi-squared test statistic, which means we need to calculate the differences between our observed and expected values in the proper fashion. Just to be clear, column B here is what we've actually observed versus column C, which is what we expected to observe. So for each category, we calculate the difference between what we've observed and what we expected to see. Now we square this so that the positive and negative differences don't cancel each other out. And then I divide it by, or I compare it to, what I expected to see. So this is not percent error, but you could think of it as akin to percent error versus what we expected to see. Okay? And then what I'm going to do is drag that down because I need that value for each of the data categories. So my chi-squared test statistic for the test is the sum then of this value for each category. So this is my chi-squared test statistic. And each chi-square goodness of fit test that we do is a right-tailed test, right? Because the further the observed values differ from the expected values, the larger this will be. And then our p-value, what we actually calculate is what's the probability of getting a chi-squared test statistic more extreme than what we've actually seen. Okay, so we want the right-tailed area in a chi-squared distribution with the proper degrees of freedom, which for our test, since there were 12 categories, the degrees of freedom would be 12 minus 1 or 11. So we say equals, I start calling up the chi-squared distributions, and I can actually use this guy will give me the right-tailed area. So this is what I would like to use, the chi-squared distribution right-tailed. So I tab for autocomplete, where this is my chi-squared test statistic, and I had 12 minus 1 or 11 degrees of freedom. So this is the p-value for my particular test. This is the probability of seeing observed values differ from the expected values more than what we saw. Okay? So what we've seen is not terribly unlikely based upon the assumption that murders are occurring with equal frequency per month. I'll then leave it to you to draw your conclusion for the test.